So in general chemistry, you learned about the shapes of these atomic orbitals, the s orbital, the p orbitals, and then you may have talked about when you start going into like period number 3, you can access d orbitals. So d orbitals are off limits in this class. We're just talking about s and p. And an orbital is really a mathematical equation. So if you remember the Bohr model of the atom, you have the protons, neutrons making up the nucleus, then you have these electrons, right? And at the start of quantum physics, the electron was described as a particle that orbited. So like the sun, you can think of as the nucleus, and Earth is like an electron in an orbit. So that orbit has a path. But as people like Einstein and Schrodinger and Heisenberg came along, the particle description of an electron is not entirely accurate. So it doesn't necessarily have like an orbit that a ball is following. And so what these pictures show you, this blue sphere, so that's the 1s or 2s orbital. An s orbital is like a ball, it's a sphere. And you'll notice it's defined. So you can see the edge, like the white is space, and then you cross over, there's the blue. So in terms of the mathematical equation, what it's saying is that there's the probability of finding the electron in that region of space. So while it's drawn like a sphere, it's really a diffuse like cloud. So if you start at the nucleus and you move out, there's a probability of finding it. And then as you get past a certain boundary, there's no more probability of finding that electron. So s orbitals, so s are spherical. And again, it's more of a cloud. It's not sort of defined like a golf ball, a basketball, a beach ball that has a boundary, but it's more diffuse. And as you move farther away from the nucleus, the probability of finding it decreases. The p orbitals are typically called dumbbell-shaped. So they have, these two regions, or lobes, as we would call them. They're colored different. The color just means the phase. So in mathematical terms, this could be a plus or a minus phase. The electron is not in the top or the bottom separately. It's in those lobes all at the same time. So everywhere all at once. And my point is not to confuse you with these concepts because they're pretty abstract. We're not going to talk about the math. We just want to know the shapes. S is spherical, P is dumbbell shaped. What I want to point out though is notice there's 3 of them, 1, 2, 3. They're all on the same energy level. And so we say they're degenerate. So that means same. And as we start plugging electrons in there as we move across the period, you put 1 in, then you move to the next, you put another electron, then you put the 3rd in. Then if you have a 4th p electron, that's when you start spin pairing them in the electron configuration. What I do want to point out, and what the heart of this issue is, you have x, the x-axis, the y-axis, and the z-axis. So again, these are 3-dimensional objects. And notice, so this is the y, the py, the px, and the pz. So those are the regions in space which those electrons exist. And what's shown to you now is they're sort of separate, but that's not really the best depiction of how things look. So this diagram to the right is probably a better description. So buried in there really tiny is the nucleus at the center. Then you have the 1s orbital, that's sort of the blue sphere. The 2s orbital is larger, the larger sphere. It's, I don't know, maybe green sort of looking. Then you have the 2p orbitals on the different axes, so y, x, and z. And then the largest sphere is the 3s. So maximum in this class, again, we'll talk about up to level 3. When we get into things below nitrogen and oxygen, so for example, phosphorus and sulfur, we'll look at some of those compounds. But again, so there's your 1s, your 2s, your 2py, 2px, and 2pz. They're not separate. Again, they're sort of all existing on top of one another. But notice the probability of finding those electrons is sort of only defined in specific regions of that space. So the atomic electron configuration of carbon is 1s2, 2s2, 2p2, that's 6 total electrons, 2 plus 2 plus 2. We don't use the core electrons, so those are not used in bonding. So that means carbon has 4 valence electrons, 2s2 and 2p2. We already said that when an electron goes into an orbital, it's unpaired, the second electron goes in, and now it's spin paired. So, for example, this orbital, we would draw something like that. You have a spin up and a spin down. Then for the 2p, you have 2 of those electrons. So there's one. The second one goes into the next degenerate orbital. Now the issue is of these 4 valence electrons, 2 of them are already paired, 2 are unpaired. So how do we explain why carbon can then form 4 bonds if 2 of them are already spin paired? They do not want to bond. The other issue is the axes in which these p orbitals reside in the atomic description do not fit what we see in alkanes, alkenes, and alkynes. So something has to happen to these atomic orbitals to change them to fit the bonding patterns that we observe. So again, here is your typical 3-dimensional Cartesian coordinate that you learn in math. There's your x-axis, your y-axis, and then if you get into calculus, you'll talk about the z-axis to figure out areas and volumes of 3-dimensional objects and whatnot. So keep in mind that the molecules we're talking about, even though we draw them flat, are 3-dimensional. So the p orbitals, these axes are 90 degrees to one another. So you have all these combinations, y to z, x to z. So they're all 90 degrees. So if you try to bond something to carbon, that's basically going to form a 90-degree angle, and that is not what we observe. So the quantum physicists, back at the early of the 1900s figured out, okay, this doesn't fit the description, so we have to do something else. So we have these 2 core electrons we're not considering, the 4 valence electrons. 2 are spin paired, 2 are unpaired. There's an issue there. They reside in orbitals that don't fit the bond angles we observe in molecules. And so of the 4 valence electrons, 2 are already spin paired. So we have to do something. And that something is, it's a mathematical operation. And as chemists, we call it hybridization. So we take the atomic s and p orbitals, we mix them together to form hybrid orbitals. So the hybrid orbitals are mixed to form sp3, sp2, and sorry, this should just be sp. So they form 3 different hybrid orbitals, sp3, sp2, and sp. So everyone in this room is kind of a hybrid. You have 2 parents, right? A mom and a dad, and they pass the genetic information on to you. So you're a mixture of your parents. And then if you have kids, they will be a mixture of you and your significant other. So these atomic orbitals, as they hybridize, the shapes will kind of change a little bit. So let's look at just pictorially what's happening. So on the left here, we have atomic carbon. There's the 6 electrons, the 1s2, the 2s2, and the 2p2. We know from general chemistry, we can start filling in those electrons in these atomic orbitals. So here's our 1s. That can only accommodate 2. We put them in, we spin pair them. Those are the core electrons. Now we have the 4 valence electrons. We move up to 2s. That can accommodate 2, so they're spin paired. Then we get up to the 2p. So remember, there's 3 of them on the different axes, x, y, and z. Since there's 2, we put them in degenerate orbitals before spin pairing them. So that's the Pauli exclusion principle. And notice this E, that's energy. So energy is increasing as we add those electrons to the atomic orbitals. So then I have this blue line that's separating atomic carbon from the functional groups we've learned, alkane, alkene, and alkyne. And you can tell right away that the carbons are all different. The alkane is showing 4 sigma bonds. The alkene, 3 sigma bonds plus 1 pi bond. And the alkyne, 2 sigma bonds plus 2 pi bonds. To form those different things, we have to use those 2s and 2p atomic orbitals to mix. So they're going to mix differently to describe these bonding patterns. So again, hybridization. The first hybrid orbital is called sp3. So we're taking the 2s orbital in all 3 of the 2p orbitals. That's what the 3 means there. So if we count, we have s plus p plus p plus p, that's 4. So when this hybridization happens, look, we get 1, 2, 3, 4 sp3 type orbitals. Notice that relative to this line E, the energy, it's sort of the average between the 2s and the 2p. So those are higher, those are lower. You mix them and they end up somewhere in between. If we draw a line over to the energy. So we have 4 sp3 type orbitals. And now what we can do is take those paired electrons from the 2s orbital, we can unpair them, and then each individual orbital here gets an unpaired electron. So 1, 2, 3, 4. That then allows us to form 4 sigma bonds. And we're representing the sigma bonds just by this single line. So that's a sigma bond. That's a sigma bond. See how that looks different? We call that a wedge. That just means in 3-dimensional space, it's projected towards you. The dash, that's also a sigma bond. That means it's projected away from you. So that's how we sort of cheaply diagram 3D space for these structures. Notice the 1s orbitals are staying the same. We're not dealing with them. They're not involved in the bonding. The next hybrid orbital is sp2. So that's s plus p plus p. The remaining third p orbital, notice it's still at the same energy. It remains unchanged. So it's not used in this mixing process. That's going to form 3, so 1, 2, 3 sp2 type orbitals. And then 1 p orbital that's left alone. So we count our electrons, 1, 2, 3. Those are going to form the 3 sigma bonds. The p orbital that's left alone is going to match up with another p orbital on a second carbon to form a pi bond. So a pi bond is made up of 2 p orbitals, each carbon donating 1. And then finally, the last type of hybridization is just sp. 1 s orbital, 1 p orbital. 2 of them remain unhybridized. So we have 2 that form sigma bonds and 2 that form pi bonds. Now keep in mind, remember that these p orbitals are on different axes. So when the pi bonds form, the pi bonds are going to be 90 degrees to one another. And I'll show that with this model on the overhead when we look at, those orbitals. So to recap on this slide, when you're looking at a structure, if you see 4 sigma bonds to carbon, that hybridization is sp3. If you see 3 sigma bonds plus a pi bond, that's sp2. 2 sigma, 2 pi, that's sp. And then what is this last row here, %s character? There's 4 total orbitals. If you take 1 divided by 4, you get 25. 1 divided by 3, you get 33. And then 1 divided by 2, you get 50. And really, the way that translates is, remember, the s orbital is spherical, the p orbital is dumbbell-shaped. So it just influences sort of the length of the bond and the size, how it looks. Any questions before we go to the next slide? Yep.
Underneath where it says atomic carbon, are the electrons on 4 different lines because of the carbon that has 4 domains?
So right here, or right here?
Where do you
Right here. So in atomic carbon, remember that, and this is the abstract part that's hard to visualize. you sort of have one ball, that's your 1s. Then on top of that is your 2s. And then in between all that are your p orbitals on the different axes. So those electrons are all in that region of space. They're not separated as sort of the prior pictures show. Yeah.
For the alkenes, you say it became flat?
Yeah, we'll talk about the overall shapes, how hybridization influences the bonding, number of bonds, and then how that influences the shapes. So there's a couple slides on that. So here are some pictures ripped out of your textbook here. Alkane, alkene, alkyne. Remember, we want to commit this one to memory, CnH2n plus 2. That's important for us. If for any n number of carbons, if you don't have the maximum number of hydrogens, then we say the molecule is unsaturated. And it's either unsaturated with a pi bond or a ring. So an sp3 hybridized carbon. So this carbon in the middle here, this is now how the sp3 hybridized orbital looks. It's like if you're taking one of the p lobes and making it bigger while the other one shrinks. So that's the shape. I know it's crudely drawn, but one sort of lobe is where the electron density is greater. But you also have this teeny tiny thing at the bottom here, or the opposite side of it, where there's still electron density, just not much. So it turns out if you take 4 sort of sticks and arrange them in space to maximize the distance between them, the shape that you get is traced out in black here, and that's called tetrahedral. So the 4 sigma bonds are in a tetrahedral arrangement or shape. And that's to maximize the distance between the bonds. And so, as I've drawn here, we see there's 2 carbons, 6 hydrogens, so that's ethane. If you take 1 carbon plus another carbon and bond them together, you have the carbon-carbon sigma bond. That's the overlap of 2 sp3 hybridized orbitals. And then every other CH bond, there's your sp3 orbital, there's your hydrogen orbital, that forms a CH sigma bond. So overall, it's going to have this shape here. And again, I have a separate slide where I'll redraw these things. But you can see each carbon is tetrahedral. So now the alkene has a degree of unsaturation, that's the pi bond. So you have that p orbital on this y-axis that's left alone. And then you have these hybrid sp2 orbitals. So it turns out when you take 3 things, you stick them in a plane and you maximize their distance. The word we would use to describe this is trigonal, so that's 3 planar. So sp2 hybridized carbon is trigonal planar. When the two carbons bond to one another, that's the central sigma bond. That second line of the pi bond is the overlap of the p orbital with the other p orbital. And really it forms a cloud. So you have these clouds. There's the two p orbitals. And then this thing in the middle here, that's the cloud on the top and the bottom of that sigma bond. And then you have your other now CH bonds that are sp2 hybridized. And our last hydrocarbon functional group was the alkyne. So now you have 2 pi bonds, so 2 degrees of unsaturation. So the difference is you're left with 1 p orbital, and then on a separate plane, 90 degrees, the second p orbital. Then you can form 2 sigma bonds. So for the C2 alkyne, acetylene, the carbons form a sigma bond to each other, and then each has a sigma bond to carbon. Then the p orbitals in one plane form a pi bond, and then 90 degrees to that, the second set of p orbitals form a second pi bond. So now this, you can see that they're 90 degrees to one another. So another word we use is orthogonal. So let me write down some words here. This was trigonal planar. And then what word do you think we use for the alkyne? Linear. And again, that results in changing the shape of the molecule. So most of the, you go to the doctor, you're sick, they prescribe you a drug. Most prescription drugs, they really act by non-covalent interactions. When they go to wherever you're hurting, they go there, they do something, then they're transported to your liver. Your liver does something, then it goes to your kidney, and then it leaves your body. So those drugs do not stay in your body. So how do they know where to go, and why do they have that activity? The activity is based on the shape of the molecule. So as the shapes of the molecules change, they have different activities. So here's that slide again. Let me just go over to this so everyone can see here. So there's ethane, and visually we just count. We see 1, 2, 3, 4 sigma bonds, so that's sp3 hybridized. Then we look at the shape. You have 1, 2, 3, 4 things bonded to that carbon, so that's tetrahedral carbon. When we go to ethene, now notice it's a different shape. I'll line this up like that. So we're looking straight down the pi bond, but each carbon is supplying a p orbital. They overlap to form the pi bond. If you look at the 6 atoms, the 2 carbons, the 4 hydrogens, they all reside in one plane. So the carbon has, so the central carbon-carbon sigma bond, CH sigma bond, CH sigma bond. So 3 sigma bonds, pi bond. The carbon is trigonal planar. So overall, you've sort of gone from something that's like three-dimensional, and now this is planar, so sort of two-dimensional in a sense. But that relates to the shape, which is a product of the hybridization. And then finally, if we take the ethene to make ethine, we're removing two hydrogens. Those hydrogens we remove, they're making p orbitals. They back bond to one another, and then we get that second double bond. So you can see, looking sort of straight down, they're orthogonal. So this means 90 degrees. They're orthogonal. They're in different planes, intersecting planes. And now that molecule just has just one axis, HCCH. Just, you can draw a rod or a line straight down. So that's linear. And we'll look at some problems today of a molecule that has tetrahedral, trigonal-planar, and linear geometries that affects the shape of the molecule. Everything that we learned today for carbon hybridization, for the most part, follows for nitrogen, oxygen. Halogens are like hydrogen in their bonding. They only form one bond. So we really don't have to worry about their hybridization. But nitrogen, oxygen, those we need to think about because they will influence the shape based on their bonding patterns. So here is a slide that summarizes everything we need to know so far about the carbon type in each functional group. So what do you need to be able to do? So look at a molecule, understand that's carbon. Oop. Getting a little too fancy here with things. I feel like Tom Cruise in Minority Report, moving stuff around. So look at a structure, know what is a carbon, count the bonds, determine the hybridization. So let's rewrite our key. So 4 sigma bonds, 3 sigma bonds plus 1 pi bond, 2 sigma plus 2 pi. Carbon with 4 sigma bonds is sp3. The percent S character is just an indication of the length of the hybrid orbital. It's a sigma bond, and then maybe this thing down here is new. What is meant by free rotation? So in my left and right hands, I'm holding the carbons. That's a sigma bond. I can rotate that sigma bond. And so you're thinking like, whoopty shit, who cares? The reason this is important is when we get to module 3, so you're looking at the molecule this way. Organic chemistry, again, is very visual. You have a perspective. That's your viewpoint. So if I say, well, I don't want to look at it this way. I want to look down the carbon-carbon axis this way. And then I'm going to start rotating. And it's not evident with this because these are all hydrogens, but as I rotate, these relationships change. So keep in mind this hydrogen, and I'm holding this one. As I rotate, now that relationship's different. So being able to rotate is important. So identifying that, understanding that sigma bonds can rotate. It's freely rotating. The pi bond, essentially what that is doing is locking those two carbon atoms in place. So I can wiggle this a little bit. If I hulked out on it, I could probably break it and rotate it. But for the most part, you can't rotate it. And we talked a little bit about when you have a double bond or an alkene, these substituents coming off, they can be on opposite or the same side. They do not interconvert. They are separate compounds because this cannot rotate. And then now you have two pi bonds. This definitely will not rotate. It's pretty much locked in place. Our next column shows bond length. This number is reported in a unit of 10 to the minus 10, which is called angstroms. So 10 to the minus 10 meters. The reason that is used is just it makes a nice number to understand. So if I was saying, well, it's 0.00000 whatever, it would be harder for you to digest. So it's a nice sort of integer decimal place and then your significant figures. What trend do you see moving across? So it's decreasing. And so why do you think that is? So as you add the pi bond, that's more electron density between them. They're more attracted to one another. You add the second pi bond, they're even more attracted, so that distance between the two carbons shrinks. So the bond length is shorter. What about for the bond energy? What happens there? So this increases. And for the exact same reason, you're putting more energy between those two atoms. So you're making a stronger bond, it's harder to break. And then what do we mean by bond angle? So an angle is always defined by 3 points, in this case, the points being atoms. So H, C, C, those are the three that we'll define. So this angle for sp3 is 109. For the alkene, so H, C, C, that angle's 120. So 120 times 3 is 360, so in that you're sort of doing a circle. And then H, C, C here for the alkyne, that's 180 degrees. So that gives you a more mathematical description of how the shape differs. And then from that angle, we get what we're calling geometry or shape, tetrahedral, trigonal planar, and linear. So the alkene is trigonal planar. The bond angle is 120. The alkyne is linear, and the bond angle is 180. So that's my 41-minute introduction on atomic orbitals. Yep.
What was the degree of the alkene?
In terms of the shape. So there's a channel on YouTube by a group called Sponholz, which I've linked these videos, I think in the second page that says like screencast or something. These videos can definitely explain this better than I can in terms of what hybridization is. Each of these, there's 3 movies, each is about 25 to 35 minutes. But it's definitely worth your time viewing them. They got this like space background, the music's a little strange, but if you ignore that, they're using, animation, computer animation to visualize these orbitals and how they're oriented in space. And if you're a visual learner, this will definitely help you conceptualize the bonding patterns a lot better than I can with just drawing or sort of models. But those are linked through the Canvas page. So here's a chart that was either taken from your book or a Gen Chem book relating or generalizing bond types, electron pairs, ultimately with the shape. And so highlighted just in green, what I've boxed off are the shapes that we need to know for this class. So row 2, linear. Those are your alkynes. Trigonal planar. Those are alkenes. And tetrahedral, those are alkanes. So we're really only concerned with, bonding types of 2, 3, and 4. 5 and 6, those are other chemistry classes. So inorganic or organometallic chemistry. Notice there's these other shapes. Trigonal pyramid, as we'll see on Friday, those are for functional groups. Amines, bent or angular, those are alcohols. Things like water, so water's a bent molecule. And the reason the shapes change, now you have to consider these electron pairs, whether you have one of them or 2 of them as you do in water. So that will influence the shape of the molecule, how those substituents influence one another. Questions? Yes. So like, for example, in the alkene here, and again, what's hard to visualize or conceptualize about this? So quantum mechanics defines like light coming from as a wave or a particle. So how can something be 2 things simultaneously? Well, it depends on the math you're using to describe it. For the pi bond, it's really not a particle that's going from this side to that side. It exists in both sort of clouds all at once. But the probability of finding it outside of that decreases as you move away. So the particle is not hopping. It's here and here simultaneously. For the most part, when we draw it, that second line, you just need to understand those electrons are coming from a pi bond. So we'll review the carbon-only functional groups, and then we'll get into this molecule called gifratoxin and start asking some questions about it. So alkanes, again, the A and E tells you it's fully saturated. That's 4 sigma bonds. Now what I've shown you are 3 different compounds. We have pentane, 2-methylbutane, and 2,2-dimethylpropane. And so these are all C5H12 alkanes. So notice to the right here, I say group CH3, that's called methyl. And another way of classifying it is we use these numbers. So we say a methyl group is primary. CH2 is called methylene, that's secondary. CH is methine, that's tertiary. Carbon with no hydrogens is called quaternary. And that has the 4. So you're just looking at a carbon, and really in terms of the last thing here, counting the other total carbons bonded to it. So a primary carbon only has 1 carbon bonded to it. A secondary carbon has 2 carbons, tertiary 3, quaternary 4. So one thing you should be able to do is, given any molecule, be able to assign what class it is. At the end here, we see there's only 1 bond to another carbon, so that's primary, that's a methyl group. Carbon number 2 is secondary. You have a carbon bond, 2 hydrogens, so that's methylene. Methylene, methylene, methyl. The 2-methylbutane, so now this one's different. That carbon number 2 is tertiary. We see 1, 2, 3 carbons, a CH, so that's a methine. The 2,2-dimethylpropane, the central carbon at carbon 2, has 1, 2, 3, 4 carbon bonds, so that's quaternary. Alkenes end in ENE. They have a degree of unsaturation, so that's the pi bond. We said if it's at the end, it's called terminal. If it's not at the end, it's called internal. But now we have these other descriptors, trans or E, cis or Z. So if we put some dots on the sp2 hybridized carbon, then we look at the substituents. We have an sp3, an sp3. They're on opposite sides, so that means trans. The other case, there's the 2 sp2 hybridized carbons. Now those sp3 ones are on the same side, so that means cis or Z. And now keep in mind that with the alkene, even though they have the same molecular formula, they're constitutional isomers, these things do not interconvert because there's restricted rotation. Then the last hydrocarbon functional group, Alkynes, YNE, that's 2 degrees of unsaturation. So 2 sigma plus 2 pi. So that's why it has 3 lines between it. These can be terminal, where the CC triple bond is at the end, or internal, where it's inside the carbon chain. Yep. 2 sigma plus 2 pi. So cycloalkanes now have a ring. In the ring is a degree of unsaturation because you have 2 less hydrogens than the alkane. So the cyclo part is referring to a degree of unsaturation. You can have 3-membered rings, 4-membered, 5, 6, 7, 8, 9, 10. It can be basically be any size. And then the last type of hydrocarbon is called aromatic. What was your question?
For cycloalkanes or like in the ring, does the bonds have to be carbon or is there any other type?
When we start introducing heteroatoms, you can have a heteroatom in a ring. So, for example, this would be a heterocycle. Cycle is telling you it's a ring. Hetero is telling you there's nitrogen or oxygen or something in that ring. So it still has a degree of unsaturation. So aromatic compounds, and this is organic chemistry too, but we still need to know they're hydrocarbons. They have 4 or more degrees of unsaturation. So this one is called benzene. That has 3 pi bonds plus 1 ring is the 4 degrees of unsaturation. The other one's called naphthalene. If you go over to your grandma's house, your Meemaw's house, go in the closet, it might smell. There's probably mothballs in the closet. Does anyone have a cedar chest or cedar wood in a closet where you have your clothes? So moths like that cedar wood, and they'll eat the clothes basically. So what people do is put mothballs in there to repel the moths. And a mothball is made of naphthalene. If you've ever smelled naphthalene, it's sort of a low melting white solid. It has like a sweet smell to it. Benzene is a colorless liquid. It looks like water. It also has a sweet smell to it. But with the economy, cedar wood's pretty expensive. If you look up the cost of cedar wood, making a cedar-lined closet is probably outside everyone's budget nowadays. But it does smell nice. So alkenes, alkynes, cycloalkanes, and aromatics are the carbon-only functional groups. So let's put some of this to practice here. The molecule that's shown is called gifratoxin, and it's right in the word there. It's a toxin. It's isolated from the skin of the harlequin poison dart frog. There's the name. I'm not a biology person, so I'll butcher that name, but there's 2 carbon atoms identified, A and B. What are their hybridizations? What do you think?
C.
So C. We see that carbon A, we have 2 sigma bonds plus 2 pi bonds. So that gets us sp. Carbon B, I'll draw the hydrogen in. So there's 3 sigma bonds plus 1 pi bond. That's sp2. And so see how it's drawn? That it's drawn that way due to the bond angles, because remember, this is 120, and then this was 180. So if you're walking that path, you sort of take a bend and then you go straight. So it's interesting. I think it's interesting. Like, why does this frog have this compound? That's a pretty complex compound.
They eat most star frogs get the toxin from the bugs that they eat.
So they get it from the bugs. The bugs eat the leaves, and the plant actually makes it. So the genetics of this plant produce it, presumably because as a defense mechanism. The plant wants to live. It doesn't want things eating it. It makes this, but the bugs eat the plant. The frog eats the bugs. And then indigenous people will take arrowheads, sort of scrape the arrowhead on the frog's back, and then shoot their enemy. And these things are either paralytic reagents or they're neurotoxins. Paralytic basically means like a respiratory thing. It stops your lungs from being able to breathe, so you suffocate and die a horrible death like Joffrey in Game of Thrones. So one more question before we leave. How many sp3 hybridized carbons are there? So we got sp, sp2. So the way you want to do this, let's just start right here. That's sp3, and then we're going to walk along the backbone. So what did we count here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So our answer here is B, 15. So always try to be logical when you're classifying these things. And again, the big picture of this is, as you learn to do this, when we start learning reactions, we're going to predict exactly which carbon a reaction is going to occur on. So we'll pick up on Friday when we introduce heteroatoms.